Yeah, the title, as you see, is Estimating Information Expiry Dates of Text. And I will first give some introduction. We think there are two types of temporal knowledge. Of course, this is very crude division, but we can talk about factual knowledge, like you see examples, or a common sense knowledge that you don't have any particular person or entity, name entity, but just in general what you expect. I mean, the ordering conditions, the time sequence, and so on. So common sense versus factual. And we will focus especially on the common sense, but we also work on the factual knowledge analysis. And we can say that these are the things that humans usually infer when reasoning in using temporal common sense, like when the action is taking place usually, how long it takes, what's the order between actions, any temporal constraints. You know, for example, that brushing teeth is in the morning, and in the evening, eating lunch is around the noon, all these things, right? And in particular, we'll focus on this one. So estimating how long an action will take to be completed. That is one part of the temporal common sense knowledge, of course. And I want to give you an example to introduce this concept temporal validity, which we will research. So imagine that you see a newspaper and you see sentences in the newspaper, but that newspaper was published 1 month ago. Maybe you just stumbled upon some old news and you just read it. And you see this sentence: President of Ukraine is visiting Austria. Doesn't matter, it never happened, but imagine it did. And it's 1 month ago published, right? And another sentence: Austria is a member of the United Nations, right? And the question, which one you would still consider as true, given that it is 1 month old news? Of course, you would say that the second one, because the first one, we know, temporal common sense here again, we know that this kind of visits last probably a week max, right? Maybe short. So what is, if we portray it on a timeline, we have some message, some information. After a certain time, we just want to reason if this message is still true, still valid, right? If I see these sentences, are they valid or not? But after 1 month. And well, this is relevant to information expiry date of products. Of course, we introduce this term because how long something will be valid, we expect. And well, that's like where you have a product, we can expect when it will be not good to be consumed. And when this concept could be useful. So we have a lot about narrative understanding, story understanding of the text, a lot of processing could be helpful because you might have sentences in the story and well, the reasoning agent can understand some temporal relations then. For search engines, if you have a query that demands fresh content, you don't want to have a document that is not valid anymore. For example, Austria economy, you issue such a query and you see a document 1 year ago written, you might be suspicious, it may be not current, right? But this is all in our minds. What we need is machines to have such reasoning. And also for chatbots and robots, if we give some maybe ordered robot do certain action, robot can reason how long it may take, or the user may say, I will be doing something now, and robot can respond maybe later after some time, expected time, do something. And also filtering microblogs. So on the Twitter, for example, we have information overload and something like, I don't know what the weather is like, but spoken yesterday may not be relevant anymore, so we can just filter it out, right? So it could be useful. Same for user tracking and analysis, which is good for marketing, advertising, or in some exceptional cases of some disasters. For example, we want to know where are the users, and yeah, of course, this is a rare application, but still. We try to estimate this kind of temporal validity. You can see that we don't approach it like exactly 3 hours, point maybe 20 minutes, but rather in a more crude way by classes. Otherwise, it is difficult to do. So you have this kind of 5 classes here and some tweets which corresponds to these classes, that this information will be valid more or less during a few weeks or a few days or a few hours, right? Someone having party in the basement, okay, that's probably a few hours. Someone, I don't know, learning programming, okay, maybe a few weeks. Of course, this is all probability distribution. We can't say for sure, but yeah, we can reason on that. And by the way, this work we started First in 2018, we published in 2019, and there was a master student from Sweden University of Gothenburg. Actually, all of this is my master students there, all what I will show today. And at that time, we didn't have good, strong deep learning algorithms, so we just did our own feature engineering. Like you can see some features here, standard ones, the length of words, some LSA, which is making topics, temporal expressions in the sentences, the length, and this is very distinct feature. I will talk about it later, but as for now, we can just skip it. And we built dataset because there was no dataset, and we collected from Wikipedia, from tweets, and from news, and different sentences annotated by users. We ran crowdsourcing. As for the validity class. And some of them had temporal expression in the sentence like 2 hours ago or next week, and half of them roughly didn't have any temporal expression. And then, well, we tried this range of algorithms, some very simple ones, and also, where is it, perceptron, multi-layer perceptron. And basically we had on these 5 classes that kind of F1 score. Of course, the higher the better here. And if we converge these classes to more crude classes, we could get better results, but that is not satisfactory. Well, at that time was, but now not. Now we discovered that just with BERT, very simple approach, could already beat these values. Well, everything changes very quickly. Validity is short, the validity of our research these days. But I wanted to talk about this particular feature, which we call global temporal association. So we thought like, okay, we can have these features like some topics in a sentence or temporal expressions, but how about if we look into web or some big crawl from the web and look for any sentences associated with duration expression, like I cook a dinner for 1 hour, or I went for holidays for 2 weeks. Any sentences with these temporal expressions, but not a point expressions, but duration, like 2 weeks, 1 hour, and so on. Of course, you will not have something like I'm kicking a ball, I'm just now kicking ball for 1 second, like the impact is just 1 second, but you will still have many, and you could do some reason. We expected that. And unfortunately, when we parsed like close to 9 million sentences from Common Crawl, we found that if you take subject verb, you have these predicates, the triples or tuples here, or subject verb of the object, and count how many sentences with temporal expressions have this particular subject and verb, you see that most of them has no temporal expression. Some subject verb patterns have maybe 1, 2, and so on. So 4 even, right? How can you reason about temporal distribution if you have something like cook dinner and only 4 temporal expressions out of 9 million sentences, right? So not really good. Of course, you can still reason that cook a lunch, cook a dinner, cook a meal, it's still similar, but it is not big number. So that was not a good way. Nevertheless, we still continue this line of research with people in Japan. And we have now, because before it was like 2,000, I think, sentences. Now we have the annotated manual, almost 300,000 sentences, a bit different classes. We also put it on the Hugging Face, the model, and we are working on a demo side. But there's one type of research which is still ongoing. More interesting, more recently, we focus on conditional temporal validity inference. And let me show example to know what I mean by conditional. So let's see, there is a post on the Twitter, let's say, I'm taking a walk by the user, and then sometime later the user posts something else, like getting a cup of coffee for takeaway, right? And now the question is the post A still true after we read post B, right? You would say that, well, true, because it's just takeaway, right? And somewhere Starbucks on the way, so he's still taking a walk. But another post, C, let's say, just started preparing dinner, right? You will know now that A is no longer valid, A action finished, right? Because you have this information. And we call it like conditions to reason about validity of this. That's why it's conditional temporal validity inference. That is the definition, and well, we can portray it like this, that given one more evidence, let's say some message, but it could be also a sentence in a book, one sentence and another sentence, you reason about this validity after getting this information. And well, yeah. So as I said, it could be a tweet stream, right? We can maybe have many tweets following this target, and one of them perhaps will be such that maybe it will render the original tweet obsolete, right? So temporal validity will be finished for that. So how we approach it, so we used a well-known task in natural language processing, which is called natural language inference. That's nothing to do with time, but it has, well, a lot of applications for question answering, for example, information extraction, that you have two sentences, typically sentences, premise and hypothesis, and then you need to tell whether these premise supports, entails hypothesis, or rather contradicts, or they are neutral, right? So this is well-known task. Datasets have been built quite large. Stanford project, for example, working on that. And yeah, the examples like you see the soccer game with many males playing, and then some men are playing sports. So these two things are definitely supporting each other to sentences. And we converted this kind of concept to our task. Hypothesis premise. So hypothesis is this original tweet, let's say, and premise is additional information. And then we need the labels supported. That means this validity is still valid. Sorry, the sentence is still valid, or invalidated, finished, or unknown, we can't say. Right? So again, three classes, a bit different semantics, and fit for our temporal purpose, right? A small Asian street band plays in a city. Their performance pulls a large crowd. A woman is eating sandwich, and now she takes off her boots in her house. So that means no longer true, the hypothesis, the sentence. But there was no data set for that, so we had to use crowdsourcing, and actually we borrowed 5,000 sentences from natural language inference data set, and then asked crowdsourcing workers to write sentences that will invalidate or support or neutral for the these original sentences, roughly 10,000 sentence pairs. And we knew that from NLI task in NLP, we knew that there are some differences in the length of sentences. So we also suspected that they may be in our case, but we found that more or less the average length is okay, not so differing. And this is important because dump classifier, we just look at the length of a sentence and learn this pattern to distinguish. Then we thought, like, okay, that's temporal common sense. Probably we can't solve it with this data set. It's still 10,000 sentences, and we didn't want to pay more to have more. So we thought, how about some knowledge base out there that contains this common sense information? We checked many of them. There are something like ConceptNet, FrameNet, Wikipedia, or whatever, but the best for us was this atomic knowledge base that is quite big, 1 million. Common sense tuples, you have examples here. Many kind of obvious information that if X repels Y's attack, then what? X feels angry, X feels tired, and so on. And this is kind of cause. Maybe X wanted to save themselves, like all this. Yeah, obvious things, and you see it's not a sentence, it's actually a couple of phrases, right? A couple of words. And we focus on, because there were 23 relations, this is a couple of these relations here, labeled edges. We focus on the things which have something to do with time, like is after, is before. And yeah, similar temporal relations. And then here is the model. I will not go so much into detail. The model, just to say that, uses the text encoding using BERT, a standard way with neural network, but also uses this knowledge base, which we first actually pre-trained on all these relations. So we pick up the relations like is caused by or during. This is the head entity, the tail entity, and the relation, and we basically trained embeddings with a trans-E method that is margin-based loss ranking. So basically, this vector plus this vector must be equal to this vector. No, actually opposite. This plus this must be equal to the country. So kind of, you look for agreement between embeddings in the knowledge base. So this was a standard text-based classification and then knowledge-based classification where we model our pair of sentences using the train embeddings from Atomic on the relations from Atomic. And they were just concatenated the vectors, one from here, one from left, also element-wise multiplication and difference, and then linear classifier. We have three classes, as we remember, supported, invalidated, and neutral or unknown. And both two sentences go here and also two sentences go here, right? So one possible model which taps from the information prepared, well, manually probably in Atomic, and also uses our small data set. And also we try to check whether NLI datasets, which are text entailment datasets, could be useful for our work, even though they are not related to time, right? But still, these are big datasets. I have to check whether Stanford dataset or this multi, I forgot which one, what was the name here, but some other dataset could just use us for our task. So we trained the CME's network on these two, and also another model that is state of the art on natural language inference with these two data sets. And we did this very simple mapping that, okay, entailment in natural language inference maps to supported, or contradiction maps to invalidated and unknown neutrality. It's not perfect semantics, but yeah, we can kind of reason. And what we discovered is that, yeah, to some extent, you could here boost up accuracy, right, pre-training on these large data sets, even though they have nothing to do with time. But on a state on the other of the other model, actually with worse performance. So, well, this is useful, but maybe these kind of clever models already capture so much information that we don't need that additional one. So, well, we tested our method with combination with CME's network and boosting the results, which was good. Then we also took this best, I mean, state of the art for NLI, and also implemented our approach here. A little bit we improved, but when we used bigger model, Roberta, rather than BERT, which is trained with very good hyperparameter tuning and on a larger data set, we didn't see the improvement. So to some extent you can help, but if you have a very large model, and this was before ChatGPT and all this buzz that happens, so yeah, now probably it will be easier for the big models to solve it. Yeah, these kind of models already encompass so much information that we can't really help. But still, for simpler models, we could have better confusion matrix, right? This is a pure CME's network. This is with our trans-E added component here, and you see that the diagonal is more darker color, which means we solve this prediction better. Yeah, so improvement 28% on one class, 6% on the other, and only minimal decrease on the third class. And also we tested other solutions than trans-E. These are for knowledge graph embeddings, trans-H, complex X, but we didn't see much, well, even worse accuracy than trans-E, so we just stayed with the most well-known probably method for that. And the previous work was done with a master student from Japan, and now a master student from computer science is continuing, Georg Wenzel, and now we are thinking about not just reason if this target tweet has been invalidated or rather still is ongoing or valid, but rather how long it will be valid, or well, maybe there is shortening of temporal validity or extending temporal validity, right? Maybe here is some action and then user complains, oh, this action actually takes a lot of time, so now we know this action will be extended, right? Or rather says, I got some help to do this action and we can reason this will finish faster. Here is one example. I have a doctor's appointment in 10 minutes, which means I might have to wait for an hour. Some sarcasm here, right? And then there is another tweet coming. Imagine this was a tweet. This is always so boring. No one ever tells me how long I'm going to be here. We still don't know. Maybe temporal validity is just the same. But here, the doctor was actually on time. so glad the visit is going quickly. We know that now this waiting will be decreased, so this will probably finish faster. And then the doctor got called away on emergency, we'll have to reschedule later next week, so increased temporal validity. And of course, it's a matter of decision, how much increase, how much decrease, and here we need to build a data set. That's what we are doing now, and thinking also about the model. So we ask users, given some tweet like this, produce tweets that will shorten or extend validity, temporal validity of this tweet, right? And usually users, sorry, not users, the workers, they just go to the next class. So maybe they increase from minutes to hours, or from hours to days, but not like from minutes to, let's say, weeks, which is a bit harder. So we are still making this data set. And later we'll proceed to build a model to solve this task. And I will slowly go into conclusions, but I will have other data, not data set, but the slides to show you. So as for now, just want to say that for the temporal common sense reasoning, the three NLP tasks we focus on, which is this temporal validity period estimation, then conditional things, either inference, if valid or not valid, or decision if, how much this validity will be shortened or extended. And for the future work, we are thinking that there could be many directions, like domain-specific data sets, like for medicine or law, where you have different actions, different validity concepts, durations. Then customized for a different user, we might have a different model. Now it's kind of user agnostic model for anyone in general, but maybe some people are faster or slower in certain actions. And then there was only one tweet following, right? One follow-up tweet, but we could now consider a couple of tweets altogether, or a couple of sentences in a novel altogether to reason about some action expressed earlier in the same book. And even multimodal scenarios, because tweets might have some pictures, right, images, and then this could also be utilized. And I want to just show one more slide about this temporal factual knowledge, because I focused on the common sense knowledge. So we also work on that, and we will present this year in Taiwan at CIR conference the approach, which is equipping BERT, and BERT is kind of like a hammer tool for NLP. Everybody uses it now. It just produces vectors for words, for sentences, and then you can do everything with vectors. So we extend this BERT with temporal signals. We call it bytime BERT, being inspired by the work on weakly supervised knowledge pre-trained language model. So just to give you an idea what is done here, BERT has two pre-training tasks. One task is to guess a word, which is mask, right? So we mask a word, and looking at the surrounding words, we try to guess what the word is, right? That's what the system is being pre-trained. Of course, we talk about millions of documents. And then next task is next sentence prediction, right? So given this sentence, predict if that sentence could be next or not, right? That kind of task. And this is standard. BERT is working quite well, but it doesn't have anything with time, right? So being inspired by this research, where they actually didn't mask just any random words, but they masked name entities, we thought we can do similar things with time. Why they mask name entities? Because name entity is central often in use, right? If you force the system to predict whether it was Joe Biden or Obama or Japan or US, it will start more reasoning than if you force it to predict the word was and or who or him, right? So it's kind of knowledge-based more. And we do similar things here, but focusing, as I said, on temporal expressions. So first of all, we having a document timestamp. Let's say this is the input document, and we try to predict when this document was published. This is news articles. Maybe for cooking recipe this will not work, but for the news it does, right? So given this context, the content, we try to predict this one. And a second task, two pre-trained tasks, is that we are masking these temporal expressions, like today through Sunday. We could also mask this one, but there's only some percentage of masking. You don't mask all the words just you leave still some of them open, but more or less like this, although not in this example, or any absolute well, relative temporal expressions we mask, and the model is forced to focus on them, especially when building word embeddings, word representation. And then we tested this model on many tasks, like question answering over archives, document timestamping, guessing when the document was published. And it was always working better than BERT and even some other extensions. Why the name is by time BERT? Because there are two types of time we consider. Timestamp when document was published, and these embedded temporal expressions in the content. That is a reference time. But that is, as you see, factual knowledge, name entities and news, so not like reasoning about how long brushing teeth will take time. But I just still wanted to mention about that. So that would be all, and I'm happy to answer questions.